Guys, here we are. We're starting with a topic that is important all the way from here to from MYP5 all the way to DP2. We will start light. This is functions and equation, which is the second topic of the diploma program, and this is both in the for those who are taking Math AI as well as those who are taking Math AA. AA for analysis and approaches, AI for application and interpretation. Okay, so in this topic, the first area that we deal with is the theory of functions in general. The theory of functions starts with relations and functions. So here we go with the first lecture on this series of lectures. Okay, so in this video, we will be discussing relations, just the basic introduction of relations, and how relations are related to functions. Okay, so the inquiry questions, or the questions that are important to us here, are what is a function? We want to understand what a function is. We want to understand the characteristics of a function, the things that make up a function. We want to know how to determine if a relation is a function. So we will understand that in general, in mathematics, we talk about relations in general, and that some of the relations qualify or have some properties that make them qualify to be functions. So not every relation is a function. We want to know which ones are function and what is it that they have that make them qualify as a function. So, so how are functions different from relations in general, okay? Another thing we want to know is why it is important to know things like independent variables and dependent variables. In science, that is the term that we use, independent versus dependent variable. In mathematics, we use terms such as domain and range, or input versus output. And the last important question we want to be able to answer is why, if anything, we really need to know about this topic. What is it that is so important about the topic on functions and equation that necessitates us to go through this process? Okay, so in terms of understanding, these are the areas we will be discussing. So we will look at mathematical relation and we compare that with what we mean by relationships in general, okay? We will look at the language of relations. We will be talking about the key terms that we use in the topic, and these terms will continue to be used all the way to DP2. Also, these terms are used in mathematics as well as in the sciences, specifically physics. 3, we will learn how to represent a relation. There are several ways. I think there are 6 ways of representing a relation, and we want to look at all of them and then be able to change from one form of relation to another. So if you're given one form of presentation of a relation, can we use that to represent the relationship in another complete different form? Okay, and what are the advantages of presenting a relation in one form and not the other in terms of these 6 ways of presenting them? Point number 4, we want to look at what it means discrete versus continuous relation, okay? And then we will get into relations versus function. Before we actually go into relations versus functions, we will first look at some basic questions that help us understand this first topic or this first area. Okay, so before we begin, let's look closely at relations. So most of us, when we hear relationships or relation, we think about stuff like romantic relations. All right, this is probably what you'd refer to as a relationship. A relationship. When in this class, this is not the kind of relation we are talking about. Another kind of relation, which would be an adversarial relation, is that between guys like Tom and Jerry and so on, right? Again, this is not what we are looking at. Something closer to home is ecological relation. We all know the importance of B in the in the environment or in terms of the ecological space, all right? Without bees, what happens to our environment? And if we have them, what is their important role in the environment? So they have an effect on what goes on around the environment. Without the bees, we would probably not exist. All right? But much closer is economic relations. Okay? The idea of supply and demand is probably known by most of us. If you increase the supply, the demand reduces, and vice versa, right? So this is a basic economic theory of one type of relation. Another area in economics on relations would be stuff like cost versus value. Okay, as the cost of a commodity increases, so does its value, and vice versa. The same goes for risk and profit. So if you wanted to make a profit on some business, you increase the risk. The higher the risk, the greater is the profit, right? But of course, risking also has the effect of if things fail, then you lose all the way. So these are some of the things that are discussed, the relationships that are discussed in economics. Okay? All right. But this is more like what we want to discuss, mathematical versus and scientific relationships. So what you have here is a speedometer of a car or the car dashboard. What we see this side is discussing the engine temperature, cold versus hot. I'm not interested in that. This is talking about the fuel in the car. So at this juncture, this guy has completely filled his tank. This is talking about the distance that has been covered. All right. And this is the range of the distance he can cover given the fuel that he has. And in such a relationship, we could have the relationship between the amount of fuel that you use versus how far you can go. So if you put 2 liters, how far can you go? If you put 5 liters, how farther can you go? And so on. So we know that the amount of fuel you put in the car relates directly with the distance that you can cover. This is the kind of relation that we are talking about. But other than that, other examples of relation, other examples of possible mathematical relationship are brightness of light bulb versus distance. So if there is a light bulb in front of you, you can measure the intensity. I believe we can use our phones directly to measure the intensity of light coming out of a source. And as you move further from the source, if you look at the display on your phone, you will notice that the intensity of the light reduces. So the intensity of light depends on how far you are from the source. This particular relationship is referred to as an inverse relation, because as distance becomes bigger, the intensity becomes smaller. Okay. Another kind of relation would be temperature of air versus speed of molecules. I could demonstrate this using a simulation. If you have a container with molecules inside and you raise the temperature of the container, the molecules in the container absorb the thermal energy and convert it to kinetic energy. So that means they move faster. So clearly the speed of the molecules will depend on the temperature inside, right? It's actually, this is what the kinetic theory is about. It says that the kinetic energy of a gas molecule is actually given by a constant, which is 3/2 K. This is Boltzmann's constant time T, which is to say, as you increase the temperature, the kinetic energy of the molecules increase. So in terms of velocity, kinetic energy is a half mv squared. This is not important for mathematics right now. So we can say that the temperature is proportional to the speed of the molecules, right? Proportional to the square of the speed of the molecule. This is not really important at MYP, except for the physics student. All we need to know is that as you increase the temperature, the velocity of the molecules also increase, and that means that there is a mathematical relation between the speed of the molecules and the temperature of the gas. Okay, another potential relation, a good relation, is the value of an investment versus time duration. We've talked about this a lot in the previous topic, financial mathematics, where we saw that the value of an investment, we can write down the formula here. The value of the investment at some time t is the value of the investment right now into 1 plus, it can be minus if the value of the investment is depreciating, then this becomes a minus, but then otherwise we have I over n, where n is the how often it is compounded within 1 year, and this was power nt. So obviously the amount, the value of the investment depends on the time. The larger the value of t is, the greater is the value of that investment. Okay, so this, of course, is a mathematical relation that we will be interested. Of course, you will remember in financial math, this refers to the rate divided by 100. So if the rate is 5%, if the rate R is 5%, then I is 0.05. Okay, it is the rate divided by 100. Okay, if the investment, if in 1 year you compound monthly, then n is 12. So you'll put 12 here and 12 there. Just by the way, as we go through this topic. And again, you need to understand or see that these things are all related. The mathematical concepts that we learn relate to one another. And the skills that we learn in one area and the content are applicable in other areas as well. Right? So another potential relation is the rate of evaporation versus humidity. In a place where the humidity is high, you can sweat, but you still feel very, very uncomfortable because the sweat does not cool you as it should. Okay? Next is photosynthesis, the volume of a gas versus light intensity. So we know in biology, for those who are studying biology, I don't, in biology we know that as leaves get sunlight, they give off a gas. Well, I can't remember whether it is oxygen or carbon dioxide, but you guys will probably know that. But as you increase the light intensity, the gas that is released, the volume of the gas released becomes more, right? Like that. So that is a relationship that biology students probably study. Probably you'll write your IA on that. The temperature versus time of day. So temperature at midday is different from temperature in the evening. So the temperature at some point during the day will vary as the time progresses. So there is a direct relationship between the temperature of the day and the time of day. Okay, these are all examples of good mathematical relation. The amount of rain that falls versus the month of the year. So in January, in some countries or in some places, there is more rain in January, while in others it's greater, the rainfall is greater in June or in August, right? So what we are saying here is that there is a relation between two quantities. So here it was brightness there, which is intensity, we call it intensity, versus distance. So two things are being compared. Okay, here it is temperature, okay, versus speed of molecules. Part 3 there, it is the value of an investment, the amount of the investment, versus the time for which the investment has been running. Question 4 is the rate of evaporation, the volume escaping per second versus humidity, how humid the environment is. The last, number 5 there, it's the volume of a gas versus the intensity of light that is being shown on the leaf. Number 6, it's temperature versus time of day. Number 7 there, it's the amount of rainfall, which would be volume, okay, versus time of the year or month of the year. So there is a relationship between two things or two quantities, and this has something that we need to discuss. This is what we are talking about. Right. So if you look at that, clearly there is a relationship in some mathematical connection, there is a mathematical connection between two things, as we have seen previously, all right? There is always two things that we are relating, okay? And one of them, the two quantities that we are relating, they could be stuff that we can count, and otherwise it is something that we can measure. We can measure the height of a person with age. How does this height change with age? We can measure the temperature of a cup of coffee as it cools on the table. So when you measure, if you're measuring something, that kind of relation is different from relations where you are counting. You're counting the number of cars passing over a section of a road in a day or every hour and so on. So when you're counting, what kind of a relation is that? And when you're measuring, what kind of a relation is that? We will talk about that shortly. Okay, so here is some terminology, some of the useful terms, some of the language we'll be using as we move on. So what do we mean when we say a variable? The general symbols that we use are x and y. The two quantities that we've talked about in all those 7 examples plus the starting ones are referred to as variables, okay? The two quantities that are under a relationship, okay, or under a relation, they are referred to as the variable. So you change one and the other one changes as a result. You change the temperature of molecules in a container or the temperature of a gas in a container, and as a result their speed increase, or the pressure they exert increase, and so on. So changing temperature becomes one of the variable. The speed of the molecules becomes the other variable, right? The quantity, so then we have domain and range, okay? If we increase the amount of fuel, for example, if we increase the amount of fuel in a car, the car will travel a larger distance. So we are changing the volume of fuel and seeing the distance covered. So here is a good example of a domain and range. The quantity that we change, the domain is the quantity that we vary, okay? Sometimes called the input or the independent variable in the sciences. So in this case, we will change the amount of fuel. So the amount of fuel is the thing that we have direct control over. So when we change the amount of fuel, as a result, the distance that we can cover also changes. So the distance is depends on how much fuel that we have used, okay? So in this case, the amount of fuel becomes the domain, and the distance covered there becomes what we refer to as the range. So the range is also the output, what comes out as a result of changing the input, okay? The other thing we need to know about is the concept of ordered pairs, all right? So here, the amount of fuel we add and the distance traveled form what we refer to as an ordered pair, x, y, like a coordinate system. Okay? So we could say xi, yi. So if the speed is 0, I mean, if the fuel we put is 0, the distance we cover will be 0. If the fuel we put in is 5 liters, the distance we can cover will have increased, and so on. The more the fuel you put, the more the distance. So when we put the distance versus the fuel versus its corresponding distance, we call this an ordered pair. Okay, so the language of ordered pair is going to be crucial. The idea of domain and range is something that you already know, but we will be using it more often now that we are going through this. So here is an example with my car. My car consumes about 8 liters, anywhere between 7.4 and 8 liters per 100 kilometers. All right. And so let's try and use this to demonstrate the idea of ordered pair, right? So the amount of fuel is 8 liters for every 100 kilometers. Okay, so that means if I put 0 amount of fuel, it gives me no distance. I can't drive the car anywhere. If I put 8 liters, I can go 100 kilometers. If I put 16, which is double the 8, it doubles the distance as well. So this is what we would refer to as an ordered pair. Okay? So now we can define a relation. So in short, a relation is a set of ordered pairs. We define a relation as a set of ordered pairs. So the example that we looked at earlier of the car consuming 8 liters for every 100 kilometers. If we put this here, what you see in the dotted box there is an example of a relation. Okay, it helps us understand the relationship between the amount of fuel being used and the distance being covered. Okay. In such a case, the domain is the set of all x values. So the ones in orange or in yellow would represent the domain of this relation. Okay, the values of x represent the domain. They are the input. Okay, and the ones in blue, and this is how we represent the domain. Okay, so we put the values of x all in one line. That is called a domain. The range would be the set of the outputs, the ones in blue there, which refers to the distance that we can cover on the fuel that we put in. So that would be the range of this relation. Okay, so here we define, I talked earlier about that there are two types of relations, where we measure or where we count things. Okay, a relation in which we count, numbers are counted, the number of cars versus the time of day. So at noon, by noon, how many cars passed? By 2 p.m., how many cars had passed, and so on. So a relation where we are counting the variables is referred to as a discrete relation. Okay, so the x values will usually be in the integer values. A continuous relation is one in which the measurable relation. So the temperature can really take any value over a given domain. So the temperature of a room in winter like now could be anywhere between minus, say, 5 until, say, 7 degrees Celsius. So it could be anything in between. So we can't represent it using distinct numbers. We can't use distinct or separate numbers to represent a relation in such a case. So in such a case, the values of x will be a range of values. So when we are representing the domain, we do not represent it as a set of numbers as we did earlier. Instead, we express it with something like this. So we would say the domain starts from maybe minus 5 to 7 degrees Celsius, or whatever it is that we are measuring. So this is the difference between continuous relations and discrete relation. We will look at some of these relations as we move on and distinguish between them. Okay. Here now we start at representing relations. How do we represent relations in general? There are several different ways of showing relations, one of which we've already talked about, which was the ordered pairs. Okay, so when we represent a relation like this, this is called an ordered pair. Okay, so that's just one way of representing a relation. But we could also represent a relation using something called a mapping. What is a mapping? A mapping is simply putting the domains in one circle, one big circle or oval like that. So the values of the domain, the yellow ones, are in one oval. And then we place the values of the range on the other. Okay, and then we connect the respective values of the domain and the range, okay, the input and the output, or independent and dependent variables. So in this case, for example, we would have to draw an arrow from 0 to 0 because these two are related. When x is 0, y is 0. When x is 8, y is 100. So we will do something like that. Okay, for 8 we would have 100. For 16, we would have 200. For 56, we would have 700, and so on. And so what you're seeing here is what we refer to as a mathematical mapping. Okay, so this is a distinct way of showing a relation between some quantity x and another quantity y. It's different from the ordered pair. It's a different way of representing the same set of information as the first one. Okay, a third way of representing a relation would be a table. Now, you have done this before, so representing a relation as a table of x values and y values is something you've done before. So this is another way of representing relation. A fourth way of representing a relation is using a graph. Again, you've done this before. So in the case of the car, amount of fuel in the x-axis, the distance being covered in the y-axis. So this is the independent variable, and that's the dependent variable. If you like, you can say this is the input, and that there is the output. Okay, so for 8 liters there, I can go 100 kilometers. For 16 liters, I can go 200 kilometers, and so on. 56 liters can take me 700 kilometers, right? So that's another way of representing a relation. The fifth way of representing a relation would be an equation. So we could say the distance covered, so distance relates to the amount of fuel. So we can say the distance covered is some constant there multiplied by the amount of fuel. How did I get this constant here? I can go back. If we look at the graph there, you can see that this is a kind of, if we were to join this with a line, we should not, because this is discrete, okay, relation. If we were to do that, then the gradient of this line telling us how many kilometers per liter. Okay, so if we take this would be 700 divided by 56, or we can say here 100 divided by 8. So 100 divided by 8 is the gradient of the relationship between distance and amount of fuel. So that's why I have that 100 over 8. If you divide that, you get 12.5. So a mathematical equation can be used to represent a relation. Okay, y is 12.5x. So if I put 10 liters of fuel here, then I can travel a distance of 125. Okay, if I put 20 liters, I can travel a distance of 250. So using an equation is another way of representing a relation. And the last way of representing a relation is basically just a text statement. Okay, a car covers a distance of 12.5 kilometers per liter of fuel. That statement there is a statement that represents a relation between distance and amount of fuel. Okay, having done that, let's look at some questions and to see how the sort of question somebody might want you to answer in terms of this first area of discussion. So question 1 there says, complete the mapping diagram for the diagram shown below. Okay, so we have a diagram here for the area of a rectangle and a mapping diagram on this side. You are to complete this. So the input is the value of the length of the rectangle. Excuse. So if we change the length of the rectangle, the area of the rectangle changes as a result. So the length of the rectangle is the independent variable, or the input, okay, or the domain, if you like. And the area, the resulting area, is our output, or the dependent variable. Okay, so if x is 1, if we make x equal to 1, we put 1 there, an input of 1 there makes the area 2 times 1. So the area here is going to be a 2, right? If we put x as 2, if we change x to 2, then the area is going to be a 4. So this is here is a 4. If we change the length to 3, the area is going to be 6. And if we change the length to 4, the area is going to be an 8, like that. And so this, what you have here, is a mapping relation, a mapping to represent a relation between the area and the length x. Okay, so the area relates to the length of the rectangle like this. Okay, we could represent this as an equation, and clearly you can see that the area equals 2 times x. This would be the mathematical equation that relates the two quantities, the dependent area and the independent length. Yeah, straightforward really. Let's see another one. Let's see another one. Okay, here is a cuboid of height h. So if we change the height as the independent variable, we can see what happens to the volume. Okay, so When the height is 1, what is the volume? When the height is 2, what's the volume? I want you to try this out and complete the mapping diagram for the volume of the container. So do that, as well as writing down an equation for relating the volume and the height of the container as a relation. Okay, here are other questions which I also want you to do. Question 3 says, for each of the following mapping diagram, complete the diagram, which is to say, fill up this space here. So 1 is to 8, 2 is to 10, 3 is to 12, 4 is to what? So you can complete this down there. Also, you can complete this. And after you've completed, part 2 says, write a mathematical relation equation. So I want you to think about what mathematical relation or mathematical equation would represent each of these relations. Okay, so if you look at it carefully, you should see a pattern and then try to come up with a mathematical formula. So m equals to something times t, all right, like that. S equal to something, something times n, or plus, it doesn't really matter. So I'm going to leave that to you to try out. We can discuss it later. Next, question 4, list the ordered pairs for the mapping diagrams shown. So here is one. So we have a mapping diagram. So a relation represented as a mapping. We want to represent this as ordered pairs, okay? So this one is straightforward. Ordered pairs means coordinate, like you are representing coordinate x and y in brackets like that. So 0 goes with 4, 3 goes with 5, and so on. So if we do that, you should see 0 goes with 4, 3 goes with 5, 6 goes with 6, and 9 goes with 7. This is a set of ordered pairs that represent this relation. So these are two distinct ways of representing a relation. Okay, here is another one. Okay, you can pause the video and see if you're going to get it right, just for practice. It's a good thing to know to do this. Okay, pause the video and try to solve it for yourself. Assuming that you've done so, then this would be the ordered pair for this particular case. Okay, 5 is to 6 and 7 is to 2. Here is another one. Please pause the video and see if you can write an ordered pair for this mapping. And if you've done so, then we have 6, 1, 7, 1, 8, 2, and 9, 2. Okay, all right. Question 5. Draw a mapping diagram. So now we are doing the opposite. We are given the ordered pairs and we do a mapping. Okay, so we have a 1, 3, 5, 7, 8, 10, and 14, 16. So obviously what I need to do here is to draw an oval there to represent x, and another one here to represent y. Okay, and then all I have to do is to put the x values. The x values here will do x values 1, 5, 8, and 14. So I'd put 1, 5, 8, and 14. And on the other side, I can put my values of y, which are 3, 7, 3 there, 7, 10, and 16. 3, 7, 10, was it 10 and 16? Yeah, and then all that is left now is for me to join these with a nice little line like this. And I have with me a nice little mapping for the relation that is given here as an ordered pair. Please try the other two, draw a similar diagram. All right, we continue. Next, here is another one. Question 6. Draw a mapping diagram for each of the following cases. Attempt an equation for the relation. So to attempt an equation, you can see this is a nice straight line. If we were to join them, of course we should not, because this is a discrete relation. We have 3 and 3. We don't have 4. We don't have 3.5. We don't have 3.2. We don't have 3.001. We don't. We only have 3. Then we have 5, and so on. So this is discrete relation. We cannot join the lines with a straight line. I mean the points with a straight line. Okay. So draw a mapping diagram. If we are going to do a mapping, perhaps the best thing to start with, if we were going to do a nice mapping, the best thing to start with is to write the ordered pair. So you can see there 1:1, this one here, 1:1, 3:3, 5:5, and 7:7. So if we could write that fast, have 1:1, right, comma, 3:3, comma, 5:5, comma, and 7:7. This represents the ordered pair for this relation, excuse me. And now it becomes easy to do a mapping. So that's my x, that's my y. The x values are 1, 3, 5, and 7. The y values are 1, 3, 5, and 7. This is a 1-to-1 kind of. So 1 goes 1, 3 there, 5, and 7. Okay, that is our mapping for that diagram. Now the next part of the question says to try and find an equation for this relation. Obviously this is straightforward. 1:1, 3:3. So we could easily say that this would be y equals x, and this is the equation for this particular relation. Yeah. Keep your questions ready so you can ask them when we are done with this, after you've watched the video. This bit is straightforward, but it's an important part of the topic on the theory of function, because when we get somewhere, when we get deeper into the discussion, we will be calling back into these basic rules. We will be calling onto the basic rules to guide our path forward. Right. Here is another one which I want you to go and try out yourself. Always do the ordered pair first, then draw the mapping, and then you can think of an equation that best relates this. This is a straight line, so the best thing to do is to find the gradient, the would-be gradient. All right? Try it out and let's see what you end up with. Let me know if you need some help. And here is another question, a last question that I want you to go and try out. Okay? This is a kind of an application question about the pressure exerted by on a diver underwater. Okay? There is a research section there. Out of curiosity, I want you to go and find out this. But please answer this question and let's see what you come up with. I think this would be the end of this video presentation. I hope you liked the presentation, and I hope it is easy to follow. If there is something that did not make sense, please comment on the space below, and also bring it up in our class discussions. If you like what you've seen, please remember to subscribe and to like it, so that when we do the next part, this is lecture 1, we're going into lecture 2. When I do the second lecture, you can get it quickly onto your inbox. Okay? Thank you very much. See you in the next video.